All right, sorry for the delay. I don't know why it takes Blackboard a few minutes to figure out how to share screen, but here we go. So the first section we're going to cover is 9.3, which is solubility. We're going to talk about what solubility is, distinguish between unsaturated and saturated solutions, and we're going to identify ionic compounds as soluble or insoluble. And we're going to learn some rules on how to do that. So solubility is just the maximum amount of solute that dissolves in a specific amount of solvent. Last class, we talked about solutes and solvents. Remember that the solute is the small part added to a large part. So if you had water, a big cup of water, and you had a spoonful of sugar, the sugar is the solute. The solvent would be water. Solubility is absolutely affected by temperature. Generally speaking, the warmer the temperature, the higher your solubility is. And we'll talk about other things a little bit later that affect solubility as well. You can express solubility as grams of solute in 100 grams of solvent, which is usually water, especially in our case. So grams of solute over 100 grams of water. Unsaturated solutions, they have less than the maximum amount of solute. So you can keep adding more of your solute. So when you add salt to water, you see it disappear. That means it's unsaturated. You add solute and it disappears. Can everyone see this okay as I'm writing? Okay, good. When the screen sharing actually starts working right, it works a lot better than trying to do everything through Collaborate. So I'm sharing this, I'm sharing PowerPoint with Collaborate Ultra, and that's what you're seeing. So if this works out well, that's what we're going to continue to do it this way. So unsaturated solutions, you can keep dissolving more solute. Saturated solutions contain the maximum amount of solute that can dissolve in that volume of solvent. The clue that you have a saturated solution is that you have undissolved solute at the bottom of the container. So at that point, you kind of reach this equilibrium where you're having solute dissolve and then recrystallize. So you're going back and forth. And this equation down at the bottom illustrates that. When you're adding your solute to your solvent, it's like you're adding that salt or that sugar to the water. Eventually, you add so much that you can't dissolve anymore. And so what you're adding is, constantly being dissolved, and then you're also making more crystals. So you're going to see something down at the bottom of that cup or that beaker or whatever it is. You're going to need to know the difference between the two. So again, this image on the left, this is unsaturated. You can keep adding solute. You don't see anything in the bottom. On the right, it's saturated. You can see that there's definitely some undissolved solute there. So let's do a quick learning check. Which one is saturated and which one describes unsaturated? So A is salt disappears when put in water. Is that a saturated solution or unsaturated solution? That's unsaturated, right? Because it's disappearing. B says sugar added to a cup of water does not disappear but sits at the bottom of the cup. Saturated or unsaturated? Right. Sharadian is just getting all of the answers. Don't just leave her by herself, y'all. Help her out. So here's another learning check. It's still about solubility, but it's taking a look at some numbers. So I'll do the first one, and then you guys can do B and C. So at 40 degrees Celsius, the solubility of potassium bromide is 80 grams of potassium bromide per 100 grams of water. You're supposed to identify these solutions as either saturated or unsaturated. So A is pretty simple. There's 60 grams of potassium bromide added to 100 grams of water at 40 degrees. 60 grams and 100 grams is less than the solubility of potassium bromide. So that means it's going to be unsaturated. What about B? You have 200 grams of potassium bromide, and you're adding that to 200 grams of water. Is that saturated or unsaturated? Right, it's saturated. It's saturated. So it's got more than 80 grams for every 100 grams of water. What about C? Saturated or unsaturated? You have 25 grams of potassium bromide in 50 grams of water. Right. It's unsaturated. It's absolutely less than 80 grams of potassium bromide in 100 grams of water. It's more like the equivalent of 50 grams in 100 grams of water. So you're going to need to be able to do those kinds of questions about solubility. It seems like folks are pretty good here. Like I said earlier, we're going to talk about the effects of temperature and some other characteristics on solubility. So it's very, very temperature dependent. Most solids, you're going to increase the solubility as temperature increases. So that means when you think salt, sugar, those kinds of things, if you're dissolving it in warm water, then you're going to have more solubility than cold water. The opposite is true of gases. If you're trying to get a gas to dissolve in the water, you actually want cooler water. So solubility of a gas decreases as the temperature of your solvent increases. Same is true for the temperature of the gas. Any questions about that? So when you're dissolving a solid, you heat up the solid or you heat up the water, you're going to have increased solubility. For gases, it's the opposite. You want it to be cooler. to dissolve in water or another liquid. So like we said, the solubility of gases decreases as the temperature of the solution increases. When you look at this graph, there's on the x-axis, there's temperature. So we're increasing temperature. That's what this triangle means. And your solubility is on the y. And we're increasing solubility as we go up the x-axis. For all of these gases, oxygen, carbon monoxide, and nitrogen gas, when you start at 0 degrees Celsius, they're fairly soluble. And as you heat the solution, you get lower and lower solubility. So let's think about that with gases. Why could a bottle of carbonated drink possibly burst or explode when it's left out in the hot sun? Now, I'm not going to expect you to write out a long answer, but I want you to at least think about it for a minute, and then we'll talk about it. So why could a bottle of carbonated drink, I'm going to just say soda. I don't know if y'all say soda down here or pop, but I say soda. Why might a can of soda or something burst when it's left outside in the hot sun? We just talked about when you increase the temperature, you're going to decrease the solubility of the gas. That means that you're going to increase the amount of gas and pressure in the can. And that pressure can cause your bottle or your can to burst. So don't do it. It's a bad idea. Why do fish die in water that is too warm? Well, it's the same idea. If you increase the temperature, then you're going to decrease oxygen gas solubility specifically, because we're talking about fish. They need oxygen too, they just don't breathe air. If you decrease the oxygen solubility, then the fish don't get any oxygen, so they're going to die. And that's sad. We don't want our fishes to die. So don't heat up the ocean, y'all. It's bad. So if you don't understand how to use the logic of increased or decreased temperature and what that will do to the solubility of a gas or a solid, let me know. So if you're unsure, you can let me know. If you're good, you can say I'm good. All right, we got an I'm good. I'm going to move on. So we're going to talk more about solubility and pressure with gases. I'm going to introduce Henry's law. There's lots of laws when it comes to gases. That was, a chapter ago or so, where we did many gas laws, and there are more. So now we're going to talk about Henry's law. Solubility of a gas in a liquid is directly related to the pressure of that gas above the liquid. So when there's more pressure above the liquid, you're going to get more gas molecules dissolved in the liquid. So let's write that out. More pressure above means increased solubility. The opposite is true as well. When the pressure of a gas above a solution decreases, then the solubility of that gas in solution decreases as well. And remember, this is only for gases. You're not going to have pressure from a solid. So Henry's law is specifically about the solubility of gas. When you're rewriting your notes or you're taking other notes, if you're looking back at this lecture, make sure that you have some kind of shorthand to help you remember what Henry's law is so that you don't get it confused. I would recommend remembering one or the other. So if you can remember more pressure above, increased solubility, great. Less pressure above, decreased solubility. Hold on to one of those so that you don't have to keep rethinking about it. That's just a test-taking tip. So we talked about gas solubility. Now we're going to go back to solids. We're really only talking about ionic compounds here. So ionic compounds, they form cation and an anion when they're dissolved in water or some other liquid. Insoluble ionic compounds, ones that will not break apart in water, their ionic bonds are stronger than the polar water molecules pulling on those ions to come apart. So remember, water has the partial positive and partial negative charge, and that's how it can interact with cations and anions. Cations are positively charged and anions are negatively charged. If the draw from the positive end or the negative end of the water isn't enough to help that ionic compound break apart, it's going to be insoluble. The rules for ionic compounds in water are in this table, 9.7. You'll definitely want to have that handy when you're doing your homework. An ionic compound is soluble in water if its positive ion is one of these listed, so lithium, sodium, potassium, rubidium, cesium, or ammonium. So if you see any of those ions as part of the ionic compound, then your guess is that it's going to be soluble. If you see so remember, positive ions are cations. If you see anions that are nitrate, acetate, let me use my pointer here, so I'm just naming these. So this is nitrate, NO3 minus. Acetate is C2H3O2 minus. Chloride ion, bromine ion, iodide, sulfate. These are the ones that are going to be soluble, but there are some exceptions. So silver, lead, and mercury 1, which let me write that out because mercury 1 is a little bit weird. This Hg2 2+ is mercury 1. It doesn't like to hang out as just a single atom. They like to pair up and hang out. So they're twinsies. You'll never see mercury 1 just on its own. Okay. So the exceptions here are ones that are insoluble. If an ionic compound doesn't have at least one of the ions in the table, then it's likely going to be insoluble. So this table, keep it around. You're going to need it. I'm not going to make you memorize it. I'm going to give you the information you need for the exam. So don't worry about that. But you will need to know how to use it. So these are some examples of insoluble ionic compounds. Cadmium sulfate and cadmium sulfide and iron sulfide. In that table, we didn't see anything about sulfide. So assume sulfides are insoluble. And if you're not comfortable with the naming that we did in Chapter 6, you'll need to brush up on that, because naming, being able to read a chemical formula and read the name of the compound, you need to be able to do that in order to use the solubility rule. Here we have lead 2 iodide. Lead is one of those exceptions. So normally, things with the halides are fine, but lead, silver, and a couple other things are exceptions, and they are insoluble. So that's how you got to use these rules. Let's do some practice. So we talked about sulfates. They're typically soluble except for these exceptions, and that's part of the table. Barium sulfate is used to enhance X-rays. So it's not like they're just passing it out every time you get an X-ray. But if there's something that they really need to see well, they will give you barium sulfate to take prior to your X-ray. Hopefully you never need that, but it does exist, and there are other ways that you can enhance some of the imaging techniques by taking insoluble compounds that will fluoresce. This table is just an example of how you can use the solubility rules. I left it in here, but I'll be honest, I don't think this table is 100% helpful. It gives you reasoning for why compounds are soluble or insoluble. So if that's helpful to you, go for it. Me personally, I just think that practice makes perfect. So let's try some. We already talked about cadmium sulfate, or cadmium sulfide, in the last one. So let's start with B. Sodium sulfate. Is it soluble or insoluble? And I put the table down there for you to be able to use. We have a guess for insoluble. So this one is soluble. Couple of reasons why. If an ionic compound contains sodium as one of its ions, then it's likely soluble. It has sodium, so it's likely soluble. The other reason is that sulfates in general are soluble as well, with some exceptions. Let's try C. Lead iodide, lead 2 iodide. Soluble or insoluble? We have one vote for insoluble, another vote for insoluble. I'm going to say yes, it's insoluble. The reason is, while most halides are soluble, lead is an exception. So that means any lead with chlorine, bromine, or iodide it's not going to be soluble. Let's try the last one. That's nickel 2 nitrate. Soluble or insoluble? D, you're getting it. So that is going to be soluble. It's soluble because there's a nitrate ion. So that's how you do it. You see whether or not you have an ion that's on the table that isn't one of the exceptions. If you do, then it's likely soluble. If it's an exception or you don't see it on the table, then that means it's likely insoluble. The final thing that we can do is predict solubility. So if we take two solutions of ionic compounds and mix them together, will we make something, or will they just be hanging out as ions in solution? The way that you can figure that out, we have two solutions here. The first solution is lead 2 nitrate. The ions in that are lead 2 plus and nitrate, which is a minus. And there's a polyatomic ion, okay? That's from chapter 6 again. So the sulfate, nitrate, all those things, and their charges, that's from chapter 6. So solution 1 is going to have lead 2 ions, and it's going to have nitrate ions. Solution 2, we'll do that in light blue. Solution 2 is going to have potassium ions, and it's going to have sulfate ions. So just remember, all it is ionic compounds. We have solutions of them, which means that we've got their ions. And I'm breaking these apart and writing out what the metal ion is, the cation, and what the polyatomic ion is in this case, or the anion in this case. Once you know what each solution has, you swap anions to see if you make something that's insoluble. So we could make lead sulfate, lead 2 sulfate, and we could make potassium nitrate. So those are the two things that we'd make when they're mixed. You swap the ions to see what you make. Then you say, are either of these two things insoluble? Now I don't have the chart up here because I needed the space to write. But the chart says sulfates are usually soluble except when there's lead involved. So that means that this lead sulfate is actually going to be a precipitate, okay, a solid that forms. So that's how you use solubility rules to predict whether a solid is going to form when you add two solutions of ionic compounds. The first thing you do is swap the ion. So you take your cation from one and add the anion from the other compound. And then you pair up the other two. Okay? So that's how we got the lead sulfate, lead 2 sulfate, and potassium nitrate. Then you use the solubility rules to see whether or not you're going to just make 2 soluble compounds or if you're going to make an insoluble compound. In this case, we said sulfates are usually soluble, but with lead, it's not. Potassium nitrate, that's soluble. So the only thing we're forming here is lead 2 sulfate. Questions about that? Okay. Thank you, Dee. I appreciate it when people respond, because I just sit here sometimes twiddling my thumbs like, is everybody watching a movie? I'd like to watch a movie with my kids. Much appreciated. All right. Oh, how do I know when it's a solid? So, you know it's a solid from the solubility rules. So these rules down here, we said that we made a sulfate and we made something with a nitrate. Nitrates are usually soluble, but sulfates, when combined with lead 2 plus, is insoluble. So that's how you know that you're going to make a solid. Does that help? Okay. So I like using PowerPoint because I don't lose all of my writing. You're welcome. So I will post this annotated copy of the presentation on Blackboard, and I'll still post the video on YouTube. So you'll have both. You don't have to watch the video if you don't want to. If you just need to add something to your notes that you forgot, you'll be able to go back and put it in there. So I think this will be overall more helpful for everybody. So that was solubility. Now we're moving on to concentrations and reactions with solutions. So this is the math part. There are lots of different ways that we can talk about the concentration of a solution. But overall, what we're talking about is how much solute is there and how much solution overall is there. When we're talking about the amount of solute, so the stuff that's dissolved in something, you can measure that in grams, milliliters, or moles. The amount of a solution, you can also talk about in grams, and you can talk about it in volume with milliliters or liters, but you're not going to talk about moles of a solution. Okay, moles are only for the solute. And just as a reminder, milliliters and liters, those are volumes. Grams, that's mass. So just a refresher from like the very beginning, just in case you had a little brain fart in there, which happens to me all the time. The first way that we're going to calculate concentration is mass percent. So we're looking at the mass of the solute in grams over the mass of the total solution. The mass of the total solution is going to be the mass of the solute plus the mass of the solvent. You're going to do that division, the mass of the solute, by the sum of the masses of the solute and the solvent, and multiply by 100%. The mass percent can be used as a conversion factor, and I'll show you how to do both of those things. So let's say that we have a solution of potassium chloride. We have 42 grams of water, and we have 8 grams of potassium chloride. What I'm going to show you is how we end up with a mass percent concentration of 16%. So we said the mass of the solute over the mass of the whole solution. And we're going to multiply that by 100%. The mass of the solute is 8 grams. The mass of the whole solution is going to be the total of the potassium chloride plus the water. And after you do that division, you multiply by 100%. And with significant figures, you should get 16%. Does that make sense to everybody? The mass of the solute versus the mass of the solution? Because that's really the only thing that you can get caught up. So don't use the 42. You got to do the whole thing. Thank you. Thank you, y'all. All right. So we have this 16%. We can actually express that as a conversion factor. So let's say you want to make something that's 16% and you're trying to figure out how much potassium chloride you need to add to whatever volume of water. You need a conversion factor for that. This 16 says that there's 16 grams of potassium chloride in 100 grams of solution. So you can use that to figure out how many grams you need or how much solution total you need to make. The other conversion factor is to just flip this upside down. You could put the mass of the solution on top and the 16 grams of KCl on the bottom. So that's how you take this percentage here, the mass percent, and write it as a conversion factor. We're going to use that a little bit later. Now I want you guys to do a practice to calculate the mass percent. What is the mass percent of sodium hydroxide in a solution prepared by dissolving 30 grams of sodium hydroxide in 120 grams of water? So give that a try and put it in the chat box what you get. I'll slowly set up the problem. I'll at least start by writing out the equation you need. We got 25%. Let's see. Yeah, that's what I thought. So you should get 20%. So don't forget to add the mass of the solute plus the solvent to get the mass of the whole solution. If we were going to write conversion factors from this 20%, it would be 20 grams of sodium hydroxide and 100 grams of solution. And then the other would just be flipped, okay? Here's one more practice for you. A solution is prepared by mixing 15 grams of sodium bicarbonate and 235 grams of water. Calculate the mass percent of the solution. Oh, that's sodium carbonate. I don't know where I got bicarb from. Yeah, let's see if some other people get an answer too. But you're on point, D. Kristen, it looks like you forgot to multiply by 100. That 0.06, you multiply by 100 and you'll get 6%. So yes, it's C. Good. Another way that you can calculate concentration is the volume percent. So it's the volume of the solute over the total volume of the solution. So we're talking about milliliters or liters, okay? When we're doing the conversion factor, you're going to have milliliters of solute per 100 milliliters of solution. So it's the same type of thing, only the units are different. We're talking about milliliters. You can also have mass to volume. So mass by volume percent, we're looking at the mass of the solute and the volume of the total solution. So say that you're dissolving a solid, right? Salt or sugar or something like that. And then the volume of your solution is what you care about. You can look at the volume of the solution after you've fully dissolved everything that you care about, and you can divide the mass of the solute divided by the volume of the whole solution and multiply by 100%. The conversion factor for that is going to be grams of solute for 100 milliliters of solution. So it's a combination of the last two approaches we talked about. So let's try writing some more conversion factors. I want you to try writing two conversion factors for C, which is 4.8% mass by volume hydrochloric acid. This is a little bit harder to type, So I'll just give you a second to figure it out, and then I'm going to write it. So when you see mass by volume, you should automatically know that means grams per milliliter. A percentage is out of 100. So 4.8% is the same thing as saying 4.8 over 100. For our conversion factors, we can have 4.8 grams of HCl over 100 milliliters of solution. I abbreviate solution SOLN. Too many letters to keep writing. The second conversion factor, you flip it. You put the 100 milliliters of solution on top and 4.8 grams of HCl on the bottom. We good with that? Okay. So there's a couple more there if you're not, and you're just not saying anything, but it's just making sure you understand what a percent is and that you know the right unit for the different types of concentrations. We're going to talk about one more type of concentration, and that's molarity. That is definitely one of the favorites of biochemists like myself. We do everything with moles and molarity. Instead of talking about grams, we're talking about moles of substance. So you can convert grams to moles using a molar mass, which we've done, and I'll refresh you on. And you express the number of moles of solute over the number of liters in your solution. So moles per liter is what molarity is. So you'll see MOL over L, or fully written out, moles per liter. So a 1 molar solution has 1 mole of a substance dissolved in 1 liter. And that is the total volume. So I'll show you how to use molarity. The question is, what is the molarity of 0.500 liters of sodium hydroxide solution if it contains 6 grams of sodium hydroxide? What we have here is a mass of 6 grams, and that's our solute. We have a volume of 0.500 liters. That's our solution. What we do not have is moles. Remember that molarity, which is a big capital M, is equal to the moles of solute over the liters of solution. We don't have anything about a mole here. All we have is a mass. So the first step, we're going to have to convert the mass of NaOH, the sodium hydroxide, to moles. The way you do that is by using the molar mass. I believe we talked about that in chapter 7 when we were doing the mole calculation. So if molar mass and moles gives you the heebie-jeebies and you just want to crawl up under a blanket, let me know Don't do that by yourself. Let me know. Remember that you have to figure out the molar mass, and that means you have to go to your periodic table and figure out what the mass of a sodium atom is, an oxygen atom, and a hydrogen atom. I'm not going to go through and write all of that out. I will tell you that the molar mass that I have is 40 grams per mole. So try that in your own time and make sure that you get that too. The second thing that we have to do is use our molarity equation. So for the first step, we're going to take our 6.00 grams of sodium hydroxide and use our molar mass. We're trying to get rid of grams, so grams should go in the bottom so that it cancels. At the top, we put 1 mole of NaOH. That's what we want. When you do that math, you should get 0.150 moles. So that's for number 1. The second part, to actually answer the question, you take those moles and divide by your volume, which was given in the problem. When you put that into your calculator, you should get 0.300 molar, which is the big M, sodium hydroxide. So that's calculating molarity, starting with the mass of the solute and the volume of the solution. Raise your hand if you need me to go through that again. Okay. Our given information, we got a mass of our solute, which was 6 grams. We were also told that the total volume of the solution is 0.5 liters. We can't jump to molarity, which is what the question is asking, because we don't have anything about mole. And molarity is moles of solute over the liters of solution. So we have to first convert our mass of solute to moles. To do that, you need a molar mass. So I took the sum of what a sodium atom is, an oxygen atom, and a hydrogen atom. Add all those 3 together, and you get 40. You need your periodic table for that. To do the math for this part, you take the 6 grams of sodium hydroxide and divide by 40 grams. That will give us moles. So this is our molar mass conversion factor. You get 0.150 moles of sodium hydroxide when you do that. The second part is to actually figure out the molarity. Now that we know how many moles of solute we have, we can divide that by how many liters of solution. And that was given in the question. So you divide the moles, 0.15, divided by 0.5 liters, and that gives you molarity, which is a capital M, and you should get 0.3 if you do that on your calculator. Does that help, Kristen? Okay, you're welcome. And again, the annotated PowerPoint is going to be up on, it's going to be a PDF that I'm going to post on Blackboard. So you'll be able to go back and look at this and follow the steps along, either using just the PDF or using the video. But I would strongly recommend that when you're doing your homework, just the class participation assignment, that if the math calculations are a little much, make sure that you match up what you're doing with a problem type that we've already done. And that will help you apply what we've done in class to your homework. So I think we're going to end here with this practice. Let me see what else. Okay. So we have a couple more things. Do you guys want to do a practice, or do you want me to give you the rest of the information about molarity? So raise your hand if you want to have the opportunity to do a practice problem. We have one vote. How about this? I will give you what the answer is, and then you can work it on your own. And if you have issues, you can email me, and you can set up a different time for office hours before Tuesday, or you can just email me your work and be like, I don't know how you got that, Dr. Hefner. Either way is fine for me. But the answer for this one should be letter B. Just remember that you have to go from mass to moles using molar mass. That's the key that you don't want to miss. So just like the other types of concentrations, you can use molarity as a conversion factor. So 3.5 molar HCl can be written as 3.5 moles of HCl in 1 liter of solution, or 1 liter of solution over 3.5 moles of HCl. This chart has examples of concentrations and what they mean and what the conversion factors look like. So that will definitely be helpful to you when you're trying to write conversion factors and use them to do your homework. You can kind of use it to make sure that you're on the right track and that you have the right units. This is another problem to practice using the conversion factors. So I'll quickly put up how to do this one, and then we'll end class here. Your homework will have some of these conversions, and it'll also have some solubility questions. So I will put this up. I know we're going a little bit over time, but I want you to have this example so that you can work on your mastering chemistry homework, and you won't be lost when we reconvene on Tuesday. So I will straight up give you the answer first. It's A. I'll show you how we get there. We have how many grams of sodium hydroxide are needed to prepare 75 grams of 14% mass by mass sodium hydroxide solution. So when you see that mass by mass, you should automatically know that 14% means 14 grams of sodium hydroxide in 100 grams of solution. So this is our 14% mass by mass, okay? The question is, which conversion factor do we need to use? So that's one conversion factor. The other is 100 grams of solution over 14 grams of sodium hydroxide. We're starting with 75 grams of solution. We want to know how many grams of sodium hydroxide. That means that we want the grams of sodium hydroxide in the top. So we're going to use this top conversion factor to figure it out. when you do the math, you're going to cancel out your grams of solution and be left with grams of sodium hydroxide. And as I said already, you should get 10.5 grams as your answer. So you will have a problem like this on your homework. It won't necessarily be mass by mass, but it'll be something similar. And then you'll have a molarity question and a couple of solubility questions. If you have any questions for me right now, you can ask it. I know we're over time by 2 minutes. Otherwise, you're free to go.